Okay, ladies and gentlemen, let's put this all together. In terms of talking about the solar system and trying to make it interesting for kids, we have found that you guys teach high school kids, so they've gone through that middle school period where they're disaffected, and then they can come back in high school or they can not in high school, depending upon what you do. But one of the things that we have found is that even for middle school kids, talking about weather in the solar system and doing stuff like that actually still gets their attention. 8th graders that are difficult to reach. High schoolers, they can get their attention span back and can work with. So one of the talks that we have traditionally done is called The Worst Weather Known to Science. For high school, we can take that and put it a little bit more into context and add more structure to it and talk about comparative planetology. All right, so it's two versions of the same talk, one adapted for different audiences. Okay, so here is our planet Earth, and the idea of comparative planetology is, of course, that you are going to be looking at other planets and other things in our solar system, and you have to have a basis of comparison, as we chatted about earlier. So our basis of comparison is, of course, always going to be Earth. All right, our discussion is going to start with Earth on most of these things and then move off to other places. All right, so let's start with a basic comparison of the just basically sizes. This is a little hot. So sizes of the rocky planets and the moon. All right, you can see Earth and Venus. We've got Mars and Mercury. One of the important things about when I do these comparisons is that I try to show the planets in visible light, what the human eye mostly would see. You cannot do that for Venus. All right, this is the best view I've gotten of Venus to approximate visible light. It's actually ultraviolet. It's a little bit into the ultraviolet. Why? Because Venus in visible light is boring, even more boring than Uranus is, okay? It's basically a white disk, and nobody takes high-resolution pictures of a white disk, all right? There is one from the Messenger mission, which sort of has a partial view of Venus. It's not fully. It's really frustrating. What you will see in your textbooks is almost always the Magellan radar maps of the surface of Venus, because those are interesting. And they're usually oftenly gaudily colored with these red, greens, and blues and all over the place, which is, of course, not what Venus looks like on its surface. So cautionary on that. But you can see the sizes. Earth and Venus are about the same size. Mars is about half of that. Mercury, a third of it. And, of course, the moon here. Now, we put the moon in as an honorary rocky planet because of its size being so close to Mercury. All right, it is anomalous that Earth has such a large moon. All right, then we take to the gas giant planets. Oh, that should just say giant planets. I haven't updated this slide. All right, Jupiter, Saturn, Uranus, and Neptune. Again, those visible light colors that you saw on the pictures that we distributed earlier. And then, of course, Earth here for comparison, being about the size of the Great Red Spot. The cool thing to note here that people are always impressed at is, oh, look at how big the Saturn's rings are in comparison of this. But by putting these things at the same relative scales, you get to feel that Saturn and Jupiter are often considered gas giants. Uranus and Neptune, you will hear them sometimes called ice giants. That is a formation mechanism that these guys formed a rocky core and then accreted gas onto them. These formed a rocky core and then accreted ices and gases onto them. All right, so sometimes we call Uranus and Neptune ice giants because of the gas giants and ice giants, and the fact that I believe it's Saturn by volume is more liquid than it is than gas. I just call them giants. So you can call them gas giants, you can call them liquid giants, you can call them ice giants, depending upon how you're looking at them. But you can't get away from the fact that compared to Earth, yeah, they count as giant planets. You'll also learn when we talk about exoplanets that we talk about Jupiter-class planets, We talk about Neptune-class planets because there's a significant, and we talk about Earth-class planets in terms of the three sizes. These have become our sort of standard of measures for the three sizes of extrasolar planets. All right, moving forward, we put them all together. You get to see the definite two major categories of planets, and then we talk about the moons around them, okay? There are 7 large moons of the solar system listed here. It's funky that our moon is one of them. These, Ganymede, Callisto, Io, and Europa are around Jupiter. Titan is around Saturn. Triton is around Neptune. So we have 6 of them around giant planets, 1 of them around a rocky planet, which is what makes our moon so funky as we look at that, okay? There are, of course, about 160 moons in the solar system, if you want to be complete, but these are the 7 most important moons about them. If you want to compare them to the asteroids, all right, we will also talk about asteroids. Here is Ceres compared to the moons. So Ceres is about the size of a medium-sized moon. It's not the size of a large moon, and that's the largest of the asteroids. We also want to talk about the Kuiper Belt, largest objects in the, I'm sorry, we want to talk the asteroid belt more, sorry. So here's Ceres, here's Vesta. These are 2 of the largest asteroids that are out there. And then we got lots of smaller flotsam and jetsam asteroids. What do they look like? They look like rocks. They look like potatoes, okay? So these are significant size. These are tiny size, just a few kilometers across what's out there. Also, when we look at the asteroid belt, you can see that there's lots and lots and lots of them. This is the orbit of Jupiter. Then we have Mars, Earth, Venus, and Mercury in here. This green stuff where there's about 300,000 dots is the asteroid belt. We'll discuss that more this afternoon. Okay? For the Kuiper Belt, here is one of the largest objects in the Kuiper Belt. It's Pluto. Again, smaller than all of the 7 large moons of the solar system. And we have the Kuiper Belt, which is analogous to the asteroid belt, which is in here. The Kuiper Belt is out here, outside the orbit of Neptune. All right, it extends from about the orbit of Neptune to about 1.5 times the orbit of Neptune. And you might think, oh, well, wait a minute, we just don't see them further out. Actually, we would have seen them if they were further out. That is a relatively sharp edge out at about 50 AU thing. I sort of assumed that they would extend further out, but talking to the experts, no, they do not extend further out. All right, Kuiper Belt objects, Pluto here. Eris is probably 5% larger, maybe the exact same size. It's within the margin of error, these are the same size. A couple others, Makemake, Haumea, Sedna, Orcus, Quaoar, Varuna. And if you wonder why they have very strange names, the answer is Mike Brown has a very strange sense of humor. Mike Brown and I went to graduate school at Berkeley. He was always the oddball amongst us, and when he got to choose names, he chose goddesses of Native American tribes in California and Hawaii and so on and so forth. So you give a guy a little bit of power to choose a name for a solar system object, he can go crazy with them. All right. These are all these small icy objects, eccentric orbits out beyond the orbit of Neptune. Okay. Important point for your kids is that all of these objects here have been discovered in their lifetimes. Okay? All of these objects have been discovered since 1992. We have a new region of the solar system since 1992. All right? So that is our overview of the solar system, so we know what we're going to try and compare things against one another. All right? Got to give an overview first. All right. So let's talk about temperature, hot and cold. Okay? Baltimore does not have tremendous weather. It can get a little hot, not that cold, fortunately. The record high, even though it's 90 degrees today, the record high was 107 degrees in 1936. It doesn't get that cold, only 7 degrees below zero. So when we were talking about whether Earth has low variation in seasons, you're talking 114 degrees in Baltimore. All right, so not that bad, okay? But if we were talking real heat, where in the continent, where in the United States would you find the hottest points in the United States? All right. What would affect temperature? Desert, right? Okay.
Death Valley.
Death Valley, yes. Okay. But let's talk about geography. Where would you expect the hotter temperatures?
Farthest away from water.
Farthest away from water. Very good. What else? Closer to the equator, latitude. All right. All right. So we would expect, if it were just purely latitude, that the hottest points in the United States would be down here or down here, right? And of course, it is not. Somebody has already mentioned that the hottest point is actually over here. All right. And this is Badwater in Death Valley. It is 280 feet or 85 meters below sea level. Important point to note that it's not just latitude, but it's also altitude. All right. As you go up in the atmosphere, you go visit the mountains, right? The tops of the mountains are snow-capped. It's colder at the top of the mountains. You get down into the valley, it's warmer. Okay, you go below sea level, you can see it gets really hot. How hot is hot? Okay, well, the record temperature in the United States was recorded at Badwater. This is the thermometer at the ranger station near Badwater. You can see it goes up to 130. It actually went past that and got to 133 or 134, if I remember correctly. There's a lot of facts and figures in this talk that I can never remember all of them, so don't quote me on any single one of them. I'll check to see if I have it in my notes. I don't. Okay. So that's pretty darn hot. The hottest spot that it's ever got in the United States. Now, this is not the hottest it has gotten anywhere in the world. The hottest it's gotten anywhere in the world is in Libya. It got up to 136 or 137 degrees in Libya. Now, let me also note that the temperature, when you officially measure the temperature, it has to be measured 5 feet off the ground and in the shade. All right? So if you think about Libya and you're in the desert, okay, if you measured that actually on the sand and not in the shade, I think you would get more than 137 degrees. So that's a caveat to what we're saying in terms of the measurement of temperature. Now, you know when it gets this hot, people can get delirious and do crazy things. People can be wandering through the desert delirious. Or if you're in Badwater, you can do such a crazy thing as run the Badwater Ultra Marathon. This is one of the craziest sporting events ever. It is a marathon that starts in Badwater in the center of Death Valley and goes up over top of the mountain and finishes at 10,000 feet. The record for finishing the Badwater Marathon is just under 24 hours. It gets so hot that they have cars driving behind them because their shoes melt on the tarmac and they have to replace their shoes several times as they're running through Death Valley. All right? So you do crazy things in heat. But if that's hot, where would we expect the coldest place in the United States to be? Say what? High altitude or also northern latitudes, okay? So the mountains of Alaska would be where you would expect the coldest places in the United States to be. Where would you expect the coldest place on our planet to be? At the poles, okay? And since we don't have animals living up at the North Pole, let's take a look down at the South Pole, all right? Because they do crazy things down there as well in the cold, all right? The coldest temperature recorded was at Vostok Station in Antarctica, and it was around 130 degrees below 0 Fahrenheit, okay? Which is around 90 degrees below 0 centigrade. And this is the point where I don't memorize anything further in Fahrenheit. I switch to centigrade in my head. So the numbers that if I spew them, which may not be correct, you can always check me on Wikipedia, are going to be in centigrade from here on. But how many of you have seen March of the Penguins? Okay? Fantastic little film about trying to survive in the cold. All right, and if you've seen that, you know that these penguins actually winter over on the ice down in the South Pole, and they have to huddle together so close that the ones on the outside have to rotate inward or they will freeze to death. Okay? Now, if you're an astronomer and you look at this from a solar system perspective, You look at these guys and you say, hey, that's really what a bloody bunch of wimps. Are they really going to say that's cold, 90 degrees below degree zero centigrade? Well, let's take a look at the solar system perspective, because we talked about Mars. Now, Mars, people think about saying, hey, we should go to Mars. We should colonize Mars. Have you heard that? Right? Ideas of that? Well, Mars has no air, it has no heat, and it has no water. So it's sort of a fixer-upper of a planet. All right? And sort of to illustrate my ideas, we have sent emissaries to Mars to measure it before we go there. Okay? This is a selfie from Mars. This is a Mars rover taking a picture of itself, okay, with its camera that's on the mast in the center, looking down. There's a selfie from Mars. This was actually taken well before selfies were a thing. All right? And it has roved around Mars for several years, and it measures the temperature for us. Okay? So we want to know what the temperature is. Well, here is a graph of the temperature in the shade. Okay? Again, in the shade from the Opportunity rover. Celsius over here, Fahrenheit over here. Well, I'll go to Fahrenheit. But you can see the maximum is on order 50 degrees Fahrenheit plus or minus 20. All right, as you go across. So it gets up to 70 degrees, maybe 30 degrees. We can handle that. Baltimore's not like that, okay? The highs in the days in Baltimore can be up, you know, that's actually pretty moderate, right? But Mars's atmosphere is so thin, as I said, 1/100th the thickness of Earth's atmosphere, that every night it gets down to minus 100 degrees. It is as cold as Antarctica ever is every single night of the year. All right? So we're talking about thermal blanketing. If it gets the hot during the day, it doesn't keep it at night. Okay? So his comment, the fact that, oh, it's hot when you're in the sun and it's cold when you're not in the sun, was not so silly as it sounded. Okay? It sounded bloody obvious, right? But this is true because when you turn away from the sun at night, and Mars has approximately a 24-hour day, it freezes every single night. Okay? Well, yeah, that contrast actually occurs even greater on Mercury, because Mercury is in close to the sun and has almost no atmosphere, what we would call a trace atmosphere. And so the hot during the day and the cold during the night is really accentuated. Furthermore, because Mercury rotates in like 88 days. Yes, question?
How quickly does that temperature change?
How quickly does the temperature change? I would think that it changes relatively quickly as you go across the terminator, as Mercury rotates and you go across the terminator. But it's going to, the longer that you're in the darkness, it's still going to continue to freeze a little bit more. That would be an interesting in terms of a temperature map on Mercury, and in terms of, because you get several hundred degrees here and you get several hundred degrees below there. The temperature differential is on order 400 degrees Fahrenheit between the two. I'm sorry I used Fahrenheit again. One of the few things I have memorized in Fahrenheit. Okay, all right, so you get an even greater thing. But if you want really cold, where would you have to go in the solar system? Not a trick question. As further out, okay? And out at the edge is the Kuiper Belt. So here is a Hubble image of Pluto. This is that Pluto map. This is our disco ball. We've got a very cold disco ball, by the way. All right. This is the Hubble pixels. I'll show you them more later, okay? This is the map of Pluto from there. Pluto and the Kuiper Belt objects are out so far from the sun that the sun to the human eye would be unresolvable. All right. We can see, with the human eye, we can see the sun as a disk. All right. Our resolution is about, the human eye resolution is about 1 arc minute. Okay. When you get out to the edge of the Kuiper Belt, the sun is now unresolved to the human eye. So it is like every other star, unresolved. Now, it's the brightest of any other star, but once you get out in the Kuiper Belt, to the human eye, our sun would be just another star in the sky, unresolved star in the sky. That's a kind of cool fact. But that means it's really, really far away. It's cold. The temperature on Pluto is minus 220 degrees Celsius. Okay? So if you think that you're going to have a beach party this is not the place to try and do it. It's going to be ice covered. There are a lot of other compounds besides water that will freeze at those temperatures. In particular, methane becomes solid around minus 200 degrees. Okay? All right. So that is the Kuiper Belt out here. These are all ice balls, frozen ice balls out at the edge of the solar system. When you get out here, you're really going to be down in things. We have an artist's drawing of one. This is the object Quaoar as an ice ball, but they threw some craters in on it. This is an artistic representation of it. Of course, if you take those ice balls and you knock them out of their orbit and they come in close to the sun, what would happen to the ice balls? They would melt, all right? They would actually sublimate. They'd go from solid to gaseous. Those gases would get pushed away by the solar wind. You'd end up having a tail, and they would become comets. So, one point to recognize, the Kuiper Belt is the repository of the short period comets. Okay? Stuff that comes in here gets knocked in here, becomes part, would become short period comets. So when I made that joke earlier today about Pluto being an oversized comet, that really isn't a total joke. Because it's in the realm of the objects like the asteroids that are small and tiny and would actually become the comets, the short period comets. All right? All right, let's talk a bit about global warming. Okay, we went out to the edge of the solar system to get the cold. How are we going to get some hot? All right, well, on Earth we have a bit of greenhouse effect. All right, and so the greenhouse effect is really something that is energy balance. Okay? We want to talk about energy balance. The energy coming in from the sun has to be balanced by the energy going away. We all know this. There has to be some balance in our systems. Okay? But the point is that the energy coming in and the energy going out are in two different band passes of light. Okay? The energy comes in mainly in visible light. With visible light coming in, some of it gets reflected, some of it gets transferred and heats up the surface. Okay? The surface of the Earth doesn't radiate visible light. It is at our room temperatures, and what do we radiate? Infrared. So it comes in invisible, it goes out in infrared. The stuff that reacts with visible is different than the stuff that reacts with infrared. The greenhouse gases are the ones that absorb infrared radiation better than others. Okay? So that infrared radiation being emitted by Earth can get reabsorbed and sent back to Earth and end up acting like a blanket that heats up Earth a little bit. Okay? So we have a bit of a greenhouse effect due to the infrared absorbing gases in our atmosphere. As we talked about, carbon dioxide, water, methane, three of the greenhouse gases. There are plenty of others. Okay? Venus. Well, Venus's atmosphere has a greenhouse effect. Okay? But as we noted, Venus is just slightly closer, so it gets twice the energy per unit area. And Venus's atmosphere is much thicker. Well, the thing is that Venus's atmosphere is 97% carbon dioxide. Right? And when you've got that much carbon dioxide in your atmosphere, you have a very strong greenhouse effect that heats up the planet's surface and causes it to have, so the surface temperature on Venus is, what is it? I can't remember whether it's Fahrenheit. It'll be there in a few slides. It's about 900 degrees Fahrenheit, if I remember correctly, or about 750 Celsius or something. All right, so here it is, actually, in Kelvin. That's 750 Kelvin, 475 Celsius, 900 Fahrenheit. It's hard keeping all of these different temperature scales in your head. I've given this talk enough times that I have said those numbers enough, but I can't still remember them back and forth. Okay. All right, so as you come down through the Earth's atmosphere, it varies and it heats, and without a greenhouse effect, it would be at minus 16 degrees. But with a greenhouse effect, it's just above zero. In Celsius, of course, so the freezing point of water is zero. So it's a good thing, okay? Now, I can't say that without a greenhouse effect, we'd have frozen oceans, all right? Even with the greenhouse effect, I'm told that there were times when our oceans mostly froze, in our billion-year history. Okay, but it makes Earth's temperature more moderate by having a bit of a greenhouse effect. By having all this extra carbon dioxide in the atmosphere, Venus continues to heat up and heat up and heat up and heat up until we're at 475 degrees Celsius or 750 degrees Kelvin. Okay? Why? Earth and Venus are very similar. How did Venus get all this extra carbon dioxide in its atmosphere? Well, the Earth has the same amount of carbon dioxide as Venus. But most of Earth's carbon dioxide is in the form of calcium carbonate, or what's called limestone, at the bottom of the oceans. All right? Our carbon dioxide has precipitated out as limestone at the bottom of our oceans. If we lost our oceans, that stuff would get into the atmosphere. We'd have the same amount of carbon dioxide in our atmosphere. We'd have the same temperature profile as Venus. So Venus being slightly closer, if it was ever going to have oceans, well, it didn't retain them. It heated up and got a little bit more carbon dioxide in the atmosphere, which heated it up some more, which added more carbon dioxide to the atmosphere, and that snowballed until it became this runaway greenhouse effect. All right? So what we see on Venus could happen on Earth and probably will happen on Earth as the sun slowly heats up over its billion-year lifespan. In about 3 billion years, the sun will be about 20% hotter, all right? And it's by itself, without us doing anything, without any man-made intervention, will help to trigger a much stronger greenhouse effect. I don't know if it will go runaway before this, but as the sun goes red giant and the temperature on Earth heats up, we'll go through a Venus-like phase. It may only be short-lived because the sun's going to expand and probably engulf Earth by the time it gets to be a full red giant. But that's billions of years away. Okay? On a shorter-term time scale, we do need to take a look at the amount of carbon dioxide we're putting in the atmosphere and how it affects the global climate. Mars, as you can see, because it's got a very thin atmosphere, has a very small differential between no greenhouse effect and with the greenhouse effect there. All right, so there's our cautionary tale. All right, let's talk about rain. Rain is a fun topic. I love this picture because it reminds me of when I was a kid in the summer rains, when it's hot outside and you get into your bathing suit and you just go out and dance in the rain and have fun. Did you guys do that, or am I just a really weird kid? I had a lot of fun, all right? I really enjoyed a nice hot summer rain. On contrary, I absolutely hate a cold rain, okay? I mean, that's just, especially as I get older, you know, maybe it pulls in arthritis or anything, but cold rain is absolutely horrible. But we also have some really interesting rain on Earth. We call it acid rain, and let's explore that. So this is a plot from a bunch of years ago, about a decade ago, but it shows you the largest sulfur dioxide emission sources in the United States. And basically these are mostly coal-fired power plants in the Midwest. All right? That sulfur dioxide comes out of these coal-fired power plants, goes up into the atmosphere. You take sulfur dioxide, you combine it with water, SO2 and H2O. What do you get? You get H2SO4, sulfuric acid, okay? Very low concentrations of sulfuric acid. At these latitudes, the winds generally go from west to east. That sulfuric acid comes out in acid rain, and here is the pH balance of lakes in the United States, where green is basic and red is acidic. Okay? This is the idea of there being acid rain coming out, that there is a very, very low concentration of sulfuric acid, but from the sulfur dioxide mixing with the water, you do get some, and it changes the pH balance of the lakes, okay? And we're talking, you know, between 4.3 and 5.3 in terms of the pH. Now, it's a small problem here in the United States. It's a much larger problem where they've been using coal for centuries, longer than we have. And that, of course, is in Europe. Here you can see the sulfur dioxide emission sources, and the deforestation, the forest damage in Europe can be very, very high. because they've been burning a lot of coal. They're at the same latitudes. Things blow from west to east over here. All right? But as we discussed about Venus a little bit earlier, there's even cooler sulfuric acid rain in the solar system, and that occurs on Venus. Okay? They actually have hazy layer of sulfuric acid drops, clouds of sulfuric acid. We do get, our clouds are still mostly water. We only have a small concentration. They've got a lot of it, and they've got sulfuric acid rain continuously in the atmosphere of Venus. All right, we get a little bit, they've got a lot of it, and it's continuous, okay? The only thing that saves about this is that as you come down, the temperature goes up and up and up and up, as we showed, and the sulfuric acid evaporates before it hits the ground, okay? So while they've got amazing sulfuric acid rain, it also doesn't actually hit the ground as it does in ours. So their lakes have a regular pH balance, right? They don't actually have lakes. Okay, but that's not the most amazing precipitation in the solar system. The most amazing precipitation in the solar system occurs on this object. This is Saturn's moon Titan. It is the only moon in the solar system that has an atmosphere. Okay, when I showed you those pictures of those 7 moons, 6 of them had clear-looking surfaces. 1 was hazy. That is Titan. Titan has an atmosphere. And up here, you can see that there's some lake-like things here. All right, some dark things that sort of look like lakes. Well, if I zoom in on them, what does that look like? Does that look like a shoreline to you? That is a shoreline. But you know that this is out at the distance of Saturn, right? We said it's cold out at Saturn. Can that be water lakes? No. Okay, these are methane lakes on Saturn. On Titan, okay? And they are serious lakes because here is a lake on Titan at the same scale as Lake Superior on Earth. They have methane lakes the size of our Great Lakes, all right? Methane, as I said, goes from liquid to solid around minus 200 degrees. This is the temperature. It is on Saturn around I think it's minus 190 to be honest with you, but I can't quite remember exactly. They've got these huge lakes. And so the most amazing rain in the solar system we can see in this image of the northern pole of Titan, and you can see the clouds that will drop methane. What happens is methane is ice at the equator. It sublimates, goes up into the atmosphere, becomes these clouds. It migrates northward and precipitates out into the lakes in the northern part of Titan. And if you really want a cold rain, minus 200 degrees centigrade, that's a serious cold rain. All right, let's talk about some winds. So when we look at Earth, there are the trade winds, right? We're all used to the idea of there being trade winds, and that the trade winds, we actually have 3 different zones. We have the equatorial zone where they blow from east to west. We have the mid zones where they blow from west to east, both above and below the equator. And then we have the polar zones where they go back to being east to west. This is what's known as Hadley cell circulation, that we have 3 Hadley cells across our planet. All right, in terms of things blowing in one direction here, blowing in another direction here. All right, and if you are trying to come from Europe to North America, such as they wanted to do, you would have to go south down here in order to get the winds in your favor to get across to North America. All right, if you ever wondered why they spent a lot of time down here, okay, because that's where you would naturally end up. If you try to go across the ocean this way, the winds are against you. You have to be tacking against those winds. It's very hard to cross the Atlantic Ocean up here. It's much easier to cross it down here, which is why everyone came down here, came across, and spent a lot of time in the Caribbean. All right, that's where that is the reason for that. All right, we can see the same thing. We can see the same thing in terms of east-west winds on the giant planets. These stripes on Jupiter. One of the things about Jupiter is although its diameter is 10 times larger than Earth, it rotates in half the time. Jupiter's rotation is 10 hours. All right, 10 times larger, the 10-hour rotation means that it's got lots of rotation. Its winds, these stripes, are induced because it has east-west winds. It has multiple cells, and you can see that each stripe is going in a different direction. You've got one stripe going this way, one stripe going that way, one stripe going this way, one stripe going that way, basically. On Jupiter, that the different zones in Jupiter's latitudes are going in opposite direction. You get very, very strong winds on order, let's see, this is on order of 400 miles an hour, or 400 kilometers, 400 miles and 700 kilometers an hour, 400 miles an hour. We can get some very strong winds on Jupiter. We get even stronger ones on Saturn. You can see Saturn again. If you look in the detail, you see it has stripes on order 1,000 kilometers an hour for the winds on Saturn. Now, one of the interesting things I find is always in trying to figure out where do you measure wind speed relative to? Because on Earth we measure wind speed relative to land, right? And if it's a giant planet, what do you have to measure wind speed relative? Well, they measure it relative to the internal rotation of the planet that they can measure via the magnetic field or some such thing. All right, so it's a very good question to try and figure out, well, wind relative to what? If you measure one band versus another, you can actually get very large, even larger winds than the 1,000 kilometers per second I quote there. Okay? We look in detail to Saturn. You can start to see even more. One thing you find out about Saturn is that as you look in infrared, you can start to see more detail in Saturn's atmosphere. And I don't know what this next slide is, so I'm just going to skip it. Venus, when we looked at Venus, we saw that there was some cloud cover. If we look in more detail in Venus, we actually see a nice chevron shape there. And that chevron shape is produced by differential rotation, that it's rotating faster at the center than it is at the poles. This is actually Earth. We talked about having 3 cells. Venus has 1 global cell in terms of the rotation, the circulation within the atmosphere. You get 1 west-to-east pattern on Venus. Okay? All right. Now storms. If you've got the winds and you've got the atmosphere, there's a good chance you're going to have storms. Here on Earth, we remember Hurricane Isabel in Baltimore. It came through and provided some interesting times in 2003. But what I want you to notice from here is that the bottom of Hurricane Isabel is down here at the Florida Keys. Okay, the center of it being at the top of Florida, and then you've got the tail of it going here, North Carolina and Virginia, and on up the East Coast to the tail of it up being here near Cape Cod. So the size of this can actually be pretty large in terms of these large hurricanes. It looks even more impressive when you look at it from space. So this is a shot from the space station looking down onto, I believe this would have to be Hurricane Isabel. I wouldn't have it in the slide set. Onto Hurricane Isabel. All right? And so we think we've got some pretty big storms, right? Well, we also talked about the Great Red Spot in terms of being a storm that has lasted 4 centuries and is as large as our entire planet. But don't give the Great Red Spot too much. It's there, but this is also a storm, and this is 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 a storm. All of these ovals across Jupiter are various storms. But the one thing we want to notice is that if we take Hurricane Isabel and compare it to the size of Earth, well, it's maybe 10% the size of our planet. You look at Jupiter, and the Great Red Spot is also approximately 10% the size of its planet. So proportionately, our great storms are similar in size to these great storms. All right? What makes the Great Spot so much fun is we've been able to follow it for years. Since there is no land, it doesn't dissipate. Here are some images from Hubble of the first decade, and you can see that it has been relatively stable. If I look at, as I said, I looked in the literature. This is from Giovanni Cassini, 1677. Yes?
On the 2 slides, previous slides, when I was reading this morning, you had talked about the junior red spot.
Red Junior, yes.
Yeah. So when I was reading about it, it said that 3 white
See those three ones right there? Yep.
They combine to make the junior.
Yes.
And then it's red.
And it turned red.
Why?
Right. Okay. I don't know if I'm discussing that in this talk or not, but yes, what happened is that over the course of 4 years, these three white ovals there merged. Okay, so first two of them merged, and then the third one merged together, and they formed a larger white oval. And then in 2003, that white oval turned red. Okay, all right. So we gathered together to strengthen the storm. And the red is due to the height within the atmosphere. Okay, as that storm got stronger, the cloud layer rose higher in the atmosphere. Different molecules condense out at different levels in the atmosphere, and the spot turned red. Okay, this is the first time we'd ever seen the formation of a red spot. Okay, we've never seen this red spot appear. We've never seen that red spot disappear. Okay, it has always been there. So this is that was an amazing time for us to be able to actually study the formation of a red spot.
So this is an older photo.
This is an older photo, yes. Right, just like with the great dark spot on Neptune isn't there anymore.
Yeah, this is the one we had in the geodome.
Okay,
So when you were referring to the,
red spot junior,
I was like,
it wasn't there, right?
geodome. Right.
So this brings in the time aspect of astronomy. A lot of things in astronomy do not change on human timescales. Storms actually do change. I mean, the Great Red Spot has been there for human timescales, but the other storms have consistently changed. So that's a great point, that when you take a look at a picture of a planet, you sort of need to know when that picture was taken. All right. For Uranus and Neptune, it's almost always going to be the Voyager photos, because those are the only times we've ever been close to was Voyager 2 getting close to Uranus and Neptune. You'll see some Hubble images of Uranus and Neptune, but if they're good and clear, they're going to be the Voyager ones. For Jupiter, we've got a lot over a lot longer time period. Okay, and so this is a drawing from 1677 by Giovanni Cassini. All right, and that sure looks like the Great Red Spot. But as I said, we don't have continuous observations to do it. What we do have with Hubble has been the fact that the Great Red Spot is shrinking. So this is a 1995 image, a 2009 image, and a 2014 image. So somebody has said, oh, it's as big as 3 Earths. And I said, that's no longer true, because it has been shrinking. And I cannot tell you for sure if that is because the red spot junior is there, perhaps using up some of the energy that is coming out in the Great Red Spot. What we do know is that there is energy coming out through the Great Red Spot and through Red Spot Junior. This is an infrared image. And you can see that the 2 red spots are very bright. There is energy coming out of Jupiter's atmosphere. One of the hypotheses is that the energy that's coming out of Jupiter is moving to more southerly to lower latitudes. Okay? More towards the southern pole, putting the energy coming out through Red Junior, allowing the Great Red Spot to be smaller, so that you, again, energy balance, right? Energy coming in versus the energy generated, the energy coming out. Jupiter actually is still generating a little bit of energy due to gravitational contraction, so it does actually generate a little bit of its own energy that comes out in the infrared. Again, that's just a hypothesis. We do not know for sure. That's the cool thing about science. We keep discovering new things. All right? So we've seen the Great Red Spot. We saw the formation of Red Spot Junior. We also, in 2008, saw the baby red spot. All right? This is one we didn't see form. It just appeared when we looked at Jupiter once. But however, the Red Junior is on a different latitude, and I said everything flows east-west on Jupiter. This is at a different latitude. It's passed by the Great Red Spot several times. This one, however, was not so lucky, and we watched it over the course of the summer as it flowed in and through and got caught in the vortices and dissipated. Okay? Baby red spot is no longer there. We also learned how vicious this storm really is, because it even eats its young. All right, Saturn. As I said, we don't see many great storms on Saturn, but we do see some if you look in the infrared. You look deeper into the atmosphere in the infrared, you can start to see storms like this You can see storms here, and you can see storms here, and you can see storms here. So one of the values, again, of using infrared, of using other radiation, is that you get to see a different view, and you start to see more of a Jupiter-like structure in Saturn's atmosphere. It's just hidden invisible light, and we see it in the infrared light. I already gave this point. The great dark spot on Neptune. When you see a picture of Neptune, it's most likely going to be one of these images from 1989 when Voyager 2 went by it. This great dark spot is not there anymore. When Hubble looked in 1994, 5 years later, the great dark spot was gone. What we believe was this spot actually migrated further north. We've seen other storms that go from south to north. When they hit the equator, they dissipate away. We surmise that that is what may have happened with the great dark spot. So your kids will always, most of the public thinks of Neptune as having a giant storm on it. That was only a temporary time. Here is views of that great dark spot as Voyager passed through it. And you can see that what's interesting is it sort of has this elongation. This is only over the course of a week in terms of the changes in shape. So unlike the great red spot where I showed you changes over the course of a decade and it wasn't that huge, this was over the course of a week and it wasn't that, and it actually was much larger. All right. But we also have seen storms on Neptune grow, because one of the things to recognize is that Neptune has a 160-year orbit around the sun. Okay, we've just passed through the anniversary of Neptune making one orbit since its discovery. Okay, and that means that seasons will last for 40 years. You get 40 years of spring and 40 years of summer and 40 years of fall and 40 years of winter. And as we're going through here over this, we've seen springtime on Neptune, and we've seen the development of seasonal storms in Neptune's southern hemisphere. All right, now we mentioned dust storms. All right, and how many people saw the movie Hidalgo? Okay, Hidalgo had this one scene that where a dust storm rises up in the desert, and the guys on the horses are racing away from it. All right, and we all know that the way that computer-generated special effects have grown, you look at this and you say, that's a fantastic computer-generated storm and everything, right? And it was just so monstrously huge and everything, and you just said, okay, great, that's wonderful. But then you see pictures like this. That is an actual picture of a dust storm coming into, and bam, there goes the neighborhood. All right? There are giant dust storms on Earth. They do achieve the proportions that were shown in that movie, which surprised me. But they can get even larger. If you look at the Sahara Desert, you can get giant dust storms that send out across the Atlantic. Okay? The amount of dust storms that is kicked up can go and stream across, hundreds and to thousands of miles. But of course, if you've learned anything from this talk, if it happens on Earth, it gets exceeded elsewhere in the solar system. And for dust storms, we're talking about Mars. And so every couple of years, we take a beautiful picture of Mars as it goes through opposition, and we release it, and everyone says, ooh, ah, ah, even though our Hubble pictures of Mars are nowhere near the quality that you get when you're there. Hey, Mars is a favorite. Solar system press releases get a lot of attention no matter what. But in June of 2001, as it went through opposition, there was a dust storm brewing in the Hellas Basin down here. Hellas Basin is a giant impact crater on Mars. All right, and you can see how it's fuzzy there. Well, we came back and we took another picture in September, and the flaw in Hubble's mirror obviously came back, because Mars is now fuzzy. No, it's not a fuzzy picture. It's actually a clear picture, but of a fuzzy planet. Because Mars's atmosphere is so thin, 1/100th the density of Earth's atmosphere, a localized disturbance can grow into a planet-wide dust storm. So this is a picture of a planet-wide dust storm on Mars. It is not a totally exceptional event. They occur once or twice every decade. We have had rovers on Mars for quite some time that have had to experience these planet-wide dust storms. They last for a month or so. And the rovers, actually, they had to program a new maneuver because they would go into hibernation during the dust storm. And then a month later, when the dust storm had passed, they had all this dust on top of the solar arrays. So they had to program a new maneuver to rotate the wheels back and forth to shake off the dust on top of the rover. So they had to basically take, you know how a dog shakes off the water, right? They had to sit there and figure out how can we program the rover to shake like a little dog and shake off the dust on the solar panels. All right. We also have other types of storms, magnetic storms on the sun. We talked about the sunspots being a location of magnetic storms. In visible light, they don't look so bad, but under ultraviolet light, you can see that there's seething energy going on in there. If you look in detail at the edge of the sun, here are where the sunspots are. You can see these magnetic loops and the plasma flowing through these magnetic loops, okay? The sunspots are dark, not because they're not hot, but because some of the energy in that region is in magnetic energy, and so they are just slightly cooler than the rest of the sun. So they're dark only in contrast to the hotter regions around them. Some of the energy in that region is in magnetic energy, okay? And here you can see these magnetic fields. And also you understand how sunspots have a northern sunspot and a southern sunspot, where the magnetic field goes out and comes back in. One of these would be a north pole, one of these would be a south pole of the magnetic field going through in and around it. Now, sometimes these magnetic loops will cross and combine, and the energy will be released in that crossing event. That is a solar flare, okay? This incredible release of energy as the magnetic fields realign and producing a burst of energy. A solar flare, oops, oh, by the way, there's the size of Earth. Oops, forgot about that. A solar flare looks like this because it is just that burst of energy, okay? It is not the prominences and filaments and everything extending away from the sun. The solar flare is that burst of energy. That burst of energy, most of the time, leads to a coronal mass ejection. That causes material and particles to flow out of the sun in a huge burst of material, sending it across interplanetary space. It comes across interplanetary space, it hits Earth's magnetic fields, the magnetic fields channel them and bring it into the poles, and where it hits the poles, we get the aurora, okay? Now, we can get the aurora even without a coronal mass ejection, but it causes the really cool ones when we have the huge influx of particles. And you can see how the aurora are these streaks down, basically the charged particles coming in the magnetic field and streaking down and giving up their energy as they descend through the atmosphere. The green in this is oxygen. The red in this is generally neon in terms of the particles in our atmosphere being excited as these charged particles are giving up their energy. And it's really cool to see the aurora. Has anybody seen the aurora up on Alaska or something and really seen it? It's great. My wife and I did it sitting in a hot tub just outside Denali National Park, drinking Chardonnay, watching the aurora. I highly recommend that. But if you want an even cooler view of the aurora, you might want to go up on the space shuttle, because this is the view from space looking down on Earth's atmosphere, and here you can see the aurora and where it ends in the atmosphere. So that's one view I haven't had a chance to get, but I'm glad that the astronauts have been able to get it for us. Okay. Recognize. Oh, this is just here simply to recognize that it occurs at both the North Pole and at the South Pole, the aurora borealis and the aurora australis. Okay. Now, Jupiter. We talked about Jupiter having a huge magnetic field, okay? Well, it's further out from the sun, so the solar wind is lower, but it has such a large magnetic field, it's also going to capture those things. In visible light, we do not see them, but in ultraviolet light, we see the aurora on Jupiter, again, both north and in south. And as we talked about yesterday in ultraviolet, we can also see the aurora on Saturn. Here is that same picture I showed you yesterday of the aurora on Saturn. Here is a really cool ultraviolet image of Saturn where the ring planes are almost perpendicular to you. And so here is that ring plane, and here is a really cool image seeing the aurora on the north and the south in Saturn. Yes?
I just have a question about the auroras. So we call them here the Borealis and the Australis.
Yes.
Since they don't have continents and those ones on planets, what do they call them? North and south?
The northern aurora, the southern aurora. On other planets, we're more prosaic and basically just saying, okay, the northern aurora and the southern aurora. Okay. I don't know of any poetic names for things like this on other planets, but you know, if you want nomenclature, you can get it in spades on Mars and Venus or stuff. But yeah, this would just be northern and southern ones on Saturn. Okay. All right. As we get into more comparative, a lot of that is what we might consider weather. We get into more comparative planetology. We can start to look at other features and how they express themselves on the various planets. So let's take a look at mountains. On Earth, we can see the various mountain chains, such as the Rocky Mountains over here, the Andes Mountains in Peru, and of course the highest mountains are up in the Himalayas here, as the continent of India crashes into Asia, pushing up this huge mountain chain there. All right, so I zoom into the Himalayas here. Of course, the tallest one is right in here, I believe it is, Mount Everest, sitting up there. And the height of Mount Everest is on order 28,000 feet, if I remember correctly. So we have tall mountains here on Earth. We also have mountains elsewhere in the solar system that we visited. Okay, you go out and you go out on your family vacation, you take a picture of yourself with a big mountain in the background. Okay, well, the astronauts did that on the moon. Okay, this is Hadley Delta, Mons Hadley Delta from Apollo 15. One of the most reproduced NASA images, because the astronaut decided to salute next to the flag, and that gives it such a patriotic feel to it that people have reproduced this in lots of places. The other thing I like to point out is that, yes, this is a color photograph, okay? But take a look at the moon. All right, the moon is a black and white world. You can definitely see this as a color photograph, but the world around it is black and white. Okay, all right. So we have this is part of a mountain chain on the moon, which is called the Apennine Mountains, or the Alps of the moon. And you see a wonderful mountain chain there, but it is of course not produced by plate tectonics. This continent is not crashing into this continent. Instead, this is this region right here, which is the rim of a crater, a very old crater that probably formed several billion years ago, 3 to 4 billion years ago in terms of this crater. And what we're seeing as mountains are really the remnant rim of a crater on the moon. Elsewhere in the solar system, we have mountains. This is one of those really gaudy images of Venus that you will find in some textbooks. This is the Magellan radar maps of Venus. And you can see there is quite a varied topology on Venus. The largest ones on Venus is this region here. This is Maxwell Mons, a mountainous region of Venus that is much higher than the rest of it. So we do get mountains on Venus. They tend to be caused more by upwellings of the entire plain rather than any individual mountains on Venus. They have a little bit of volcanic activity, I'll show you in a second, but for Venus, there tends to be upwelling of lava and such, pushing up the continents in various pushing up the surface in various places, as opposed to any plate tectonics here again. All right, looking at canyons, our of course favorite canyon in the United States is the Grand Canyon. Quite a wonder. Again, lots of cool things to see when you go on vacation, going out and see the canyons. What's cool about this one is that you can actually see it from space. So here is a satellite image, and you can see the Grand Canyon here. All right, my wife and I actually started up here and did a river rafting trip down into the Grand Canyon. All right, down here to Phantom Ranch, and then hiked out to get get there. that was a really cool trip in terms of doing that. And what's really cool about it is as you're going through here, you're seeing the layers of rock, and you got all this geologic history, a couple billion years of history that you're climbing in and out of as you hike down to the bottom of the canyon. All right, and so when you see it, you can see, okay, upper northwest Arizona, you can actually see this from space. All right, we talked about other canyons. On Venus, they have these canyons much like the ones we discussed on that moon. I'm forgetting the name of the moon right now, but in terms, that's somebody's phone doing something. Okay, we have those sort of canyons, these sort of rifts, and basically the tearing of the surface, creating these canyons on Venus. We also have a Grand Canyon on Mars. All right, this is Valles Marineris, which is actually the Grand Canyon in the solar system, because instead of stretching across the corner of Arizona, we can see this from space just looking at the globe of Mars. Valles Marineris stretches across so large that you can see it on a global picture of Mars, and if we put to scale the United States, it would stretch from the west coast all the way to the east coast. Okay? So I'm going to combine two things that we just talked about in terms of that upwelling, lifting of the surface on Venus. Well, that happened over here in the Tharsis Plains on Mars. There's an uplift of the whole Tharsis Plains, perhaps leading to water flowing downhill through Valles Marineris out into these lower lands there. All right? One major hypothesis for how Valles Marineris was created was long ago, when there was water on Mars, the upwelling of the Tharsis Plains caused water to flow down, channeling out Valles Marineris as the water flowed through there. All right, a couple more things before I let you go for lunch. Volcanoes in the solar system are really cool. This is Mount Pinatubo. This is the explosion of Mount Pinatubo, sending ash well up into the air. We also, in the United States, remember back in the 1980s, Mount St. Helens. All right, this is a picture from the U.S. Geological Survey of Mount St. Helens before the eruption, and this is it after the eruption. All right, talk about blowing your top, okay? Before the eruption, after the eruption. Puts it very starkly in contrast of the amount of material that was there. And what's really cool about these volcanoes is that because they are an under-earth process pushing mostly straight up, you can get these volcanic mountains that appear as these sort of lonely mountains, okay? The plate tectonics produces these long mountain chains because it's a line across there in which you're pushing up the mountains. The volcanic processes can actually produce individual mountains. We see profiles like this on Earth. We also see a profile like that on Venus. There are evidence of volcanoes on Venus with that same sort of profile of that sort of upwelling that produces there, and also volcanoes on Mars. This is that Tharsis Plains where I talked about that the whole region around here is at a higher level, okay? Much like the Mount Everest rises from the Himalayan plateau, Mount Olympus rises from the Tharsis Plains. There are also 3 other very strong shield volcanoes. So looking in at Mount Olympus, all right, it's the largest volcano in the solar system. How big is it? Well, it is so big, it is the size of the entire state of Arizona. So we think about the Grand Canyon being big there. We talk about Valles Marineris being much bigger. Well, we got volcanoes the size of an entire state on Mars. And if you look at it in profile, how does it compare to Mount Everest? Well, there's Mount Everest, our biggest mountain, compared to Olympus Mons. All right? Olympus Mons is so large, it's actually the largest mountain you can create on Mars. Because if you put it any higher, the pressure and density pushing down on the surface would actually cause it to spread out more. So you can see it as a very wide mountain simply because you try to stack things higher, the gravity causes it to collapse and press out sideways. All right, and this, again, you can see Olympus Mons here on a global view. But of course, this is not the coolest volcanoes in the solar system. All right, this may be the biggest, but the biggest isn't always the best. The coolest volcanoes in the solar system occur on Io. Okay, Io is Jupiter's innermost Galilean moon, and it has a slightly elliptical orbit that causes it to flex. The surface of it flexes just enough to heat the inside, and it gets volcanic eruptions. Okay, this is one of its biggest volcanic eruptions, one called Pele, and you can see the circular material around this. What is being spewed out of the interior of Io is sulfur dioxide. Okay, sulfur dioxide. You can see the ring of material around Pele. All right, well, a few months later, we took another picture of it, and boom, here's a brand new one, which shows you the level of volcanic activity on Io. An average of 7 volcanoes are erupting on Io at all times. There's always volcanoes erupting on Io, and what's cool is you can see them off the limb of Io. If we zoom in on that, all right, if we think about, you know, Mount Pinatubo or the other volcanic things, we go up several miles into our atmosphere, okay, but our atmosphere is 60 miles in height, so that would never extend off the limb of Earth. But on Io, they can extend up that you can actually see them. And this leads us to the coolest image of a volcano in the entire solar system. Now, this was taken by the New Horizons mission on its way to Pluto. All right, New Horizons came by Jupiter for a gravity assist, and it did some observations, testing out its cameras and everything, and took some pictures. But this is the volcano Tvashtar on Io, a series of 5 images from the New Horizons mission, and you can see the sprinkler head of sulfur dioxide spewing off the edge of Io. All right, so there's a couple more things that I could go through, but we hit the 11:30 time limit. I don't want to keep you from your lunch. But basically, we could go on for hours about all the various comparisons in the solar system. I have some things on rivers, and I have some things on ice, on polar caps and such. All right, but the message is pretty clear that whatever we think is really extreme here on Earth, well, it happens elsewhere in the solar system to a much more extreme level. It gives you a sense of perspective on what happens here versus what happens elsewhere in the solar system. But the message I always finish with is that what that really means is that there's no place like home. Okay? If we want a place that is going to have moderate temperatures, that's going to have reasonable storms, that's going to have the kind of weather and the kind of atmosphere and the kind of hospitable nature that life can form, well, we haven't found anything elsewhere in the solar system like our Earth. All right, so the fact that it isn't the most extreme is actually a good thing. All right, so we can be glad, we can explore all these other extremes in the solar system and say, hey, this is really cool, but we can also be glad that our Earth is not the home of all of these things. All right, let's break for lunch.